Hello students, hope you all are doing good. Myself Brinda Patel, Assistant Professor in Computer Engineering Department at Sri Swaminarayan Institute of Technology. So today we are going to start new unit which is image segmentation. So the outline of this chapter is detection of discontinuities, edge linking and boundary detection and thresholding. So image segmentation is divides an image into regions that are connected and have some similarity within the region and some difference between adjacent regions. So the global is usually to find individual objects in an image. So for most part that are fundamentally two kinds of approaches to the segmentation, which are discontinuity and similarity. So the focus of this section is on the segmentation methods, which are based on the detecting sharp local changes in intensity. So three types of image features in which we are interested for the isolated points, lines, edges, and here three are the main points, which is isolated points, lines, and edges. So edges pixels are pixels at which the intensity of an image function changes abruptly, and edges are set of connected edge pixels. So edge detectors are local image processing methods designed to detect edge pixels. So a line may be viewed as an edge segment in which the intensity of the background on either side of the line is either much higher or much lower than the intensity of the line pixels. So there are three kinds of discontinuity of intensity. We know points, lines, and edges. So the most common way to look for discontinuities is to scan a small mask over the image. So the mask determines which kind of discontinuity to look for. So the approach of choice for computing first and second derivatives at every pixel location in an image is to use spatial filters. So for 3x3 filter mask in this figure is the procedure is to compute the sum of products of mask coefficient of this figure and with the intensity values in the region encompassed by the mask. So that is with reference the response of the mask at the center point of the region is R is equal to W1Z1 plus W2Z2 plus up to W9Z9, or we can, so here the limit is epsilon I is equal to 1 to 9 Wi Zi. So we illustrate segmentation of isolated points in an image with the aid of this figure here, which is an X-ray image of turbine blade from a jet engine. So the blade has a porosity in the upper right quadrant of an image, and then there is a single black pixel embedded within a porosity. So this figure is the result of applying the point detector mask to the X-ray image, and this figure shows the result of using this equation with the T equal to 90% of the highest absolute pixel value of the image in figure C. So the single pixel is clearly visible in this image. So this type of detection process is rather than specialized because it is based on the abrupt intensity changes at single pixel locations that are surrounded by a homogeneous background in the area of the detector mask. So the next level of complexity is a line detection. So only slightly more common than point detection is to find the one pixel wide line in an image. So for digital images, the only 3 point straight lines are only for horizontal, vertical, and diagonal, means plus or minus 45 degree. So consider the mask in these figures. Suppose that the image with a constant background and containing various lines so is filtered with the first mask. The maximum responses would occur image locations in which a horizontal line passed through the middle row of the mask. So this is easily verified by sketching a simple array of ones with the line of difference intensity. running horizontally through the array. So a similar experiment would reveal that the second mask in this figure responds the best lines oriented at plus 45 degree. The third mask is to vertical lines, and the fourth mask is to the lines in the minus 45 degree directions. So the preferred direction of each mask is weighted with the larger coefficient rather than possible directions. So the coefficients in each mask sum to 0, indicating a zero response in areas of constant intensity. So now for the line detection, here another figure. So here this figure shows the image used in the previous example. Suppose that we are interested in finding the lines that are 1 pixel thick and oriented at plus 45 degree. So for this purpose we use the second mask in this figure. So here figure B is the result of filtering the image with the mask. So as before, the shades darker than the gray background. This figure corresponds to the negative values. So there are two principal segments in the image oriented in the plus 45 direction, one at the top left and one at the bottom right. So this figure shows the zoomed section of this and corresponding to these areas, right? Now edge detection, this edge models. So edge detection is the approach used most frequently for segmenting images based on abrupt changes in the local changes in an intensity. So the edge models are classified according to their intensity profiles. A step edge involves a transition between two intensity levels occurring ideally over the distances of 1 pixel. So here in these figures, figure A shows the section of a vertical step edge and a horizontal intensity profit through the edge. So digital image have edges that are blurred and noisy, with the degree of blurring determined principally by limitations on the focusing mechanism. So and the noise level determined principally by the electronic components of the imaging system. In such situations, edges are more closely modeled as having the intensity rep profile, such as here. So the third model of an edge is so called a roof edge, having the characteristics illustrated here. So the roof edges are models of lines through a region with the base means width of roof edge being determined by the thickness and sharpness of the line. So this figure A shows the image from which the segment in here figure B was extracted. So this figure shows the horizontal intensity profile. So this figure shows also the first and second derivatives of the intensity profile. Moving from left to right along the intensity profile, we note that the first derivative is positive at the one set of the ramp at the points on the ramp. So it is 0 in areas of constant intensity, right? So the second derivative is a positive at the beginning of the ramp, negative at the end of the ramp, and 0 at the point on the ramp, and 0 at the point of the constant intensity. So here the image segments in the first column shows the close-ups of 4 ramps edges that transition from black region on the left to a white region on the right. Keep in mind here that the entire transition from black to white in a single edge. So the image segment at the top left is free noise. Here this 3, 1, 2 and 3. So these 3 images in the first column are corrupted by the additive Gaussian noise with 0 mean and standard deviations of 0.1, 1.0 and 10.0 intensity levels respectively. So here the graph of each image in a horizontal intensity profile passing through the center of the image. All the image have 8 bits of intensity resolution with 0 and 255 representing 0 and 255 representing black and white respectively. Now here for the gradient operators, so it is a basic edge detection. So detecting changes in intensity for the purpose of finding edges can be accomplished using first or second order derivative. So the image gradient and its properties are here. So the tool of choice for finding edge strength and direction at location of xy of an image f. So it is a gradient denoted by del f and defined as the vector del f is equal to grade of f is equal to gx gy is equal to del f upon del f upon del x and del f upon del y. So this vector has a important geometrical property that it points in a direction of the greatest rate of change of f at location of xy. So the magnitude length of vector del f, so mag del f is equal to gx square gy square raised to 1 by 2, or we can say root of gx square and gy square. So it is a value of the rate of change in the direction of the gradient vector. So note here that gx and gy and m of xy are images of the same size as the original created when x and y are allowed to vary over all pixels location in f. So it is common practice to refer to the latter image as the gradient image or simply as the gradient when the meaning is clear. So the summation, square and square root operations are array operations here. So which are alpha xy is equal to tan inverse gx of upon gy. So it is measured with the respect to the x axis. As in the case of gradient image, alpha xy also in an image the same size as the original created by the array division of image gy by image gx. So the direction of an edge at an arbitrary point of xy is a orthogonal to the direction alpha xy of gradient vector at the point. So it points in the direction as the greatest rate of the change of f at location xy. This figure shows a zoomed section of an image containing a straight edge segment. So each square shown corresponds to a pixel and we are interested in obtaining the strength and direction of the edge at the point highlighted with the box. So the pixels in gray have value 0 and the pixels in white have value 1. So we show here that an approach for computing the derivatives in x and y directions are using 3 by 3 neighborhoods centered about a point consists simply of subtracting a pixels in the top row of the neighborhood from a pixels in the bottom row to obtain the partial derivative in the x direction. So here are the gradient operators. So when a diagonal edge direction of interest, so we need a 2D mask, 2-dimensional mask. So the Robert Cross gradient operators are one of the earliest attempts to use 2D mask with the diagonal preferences. So consider here the 3 by 3 region. So here mask of size 2 by 2 are simple conceptually, but they are not as useful more computing edge direction as mask that are symmetric about the center point, the smallest of which are the size of 3 by 3. So these masks take into account the nature of the data on the opposite sides of the center point and thus carry more information regarding the direction of an edges. So the simplest digital approximations to be partial derivative using the mask of 3 by 3. So here these masks are known as Pratt-Whit operators and these are the Sobel operators. So in this, the here the difference between the third and first row of the 3 by 3 region approximates the derivative in the x direction, and the difference between the third and first column approximate the derivative in a y direction. So here we would expect their approximations to be more accurate than the approximation obtained using a Roberts operators. So these marks are known as a Prewitt marks for the detecting diagonal edges, and here these masks are known as a Sobel mask for detecting diagonal edges. So this figure illustrates the absolute value response of the two components of gradient gx mod gx and mod gy. So here the gradient image formed from the sum of these two components. So the directionality of the horizontal and the vertical components of the gradient is evident here in B and C. So for example, how strong the roof tile horizontal brick joints and horizontal segments of the windows are, we can see here, compared to the other edges, right? So by the contrast here, this figure favors a feature such as a vertical component of facade and windows. So here this figure shows the same sequence of an image as here, but with the original image smoothed first using 5 by 5 averaging filter. So the response of each mask now show almost no contribution due to the bricks, with the results being dominated mostly by the principal edges. So here this figure A and B here shows the absolute responses of 45° and -45° Sobel mask respectively. So the stronger diagonal response of these masks is evident in these figures. So both diagonal masks have similar response to horizontal and vertical edges, but their response in these directions is weaker than the response of the horizontal and vertical mask. Now, edge linking and boundary detection in global processing via Hood transform. So the edge detection should yield sets of pixels lying only one edges. In practice, these pixels seldom characterize edges completely because of noise breaks and in the edges due to uniform illumination. So and other effects that introduce superior discontinuities in intensity values. So therefore edge detection typically is followed by linking algorithms designed to assemble edge pixels into a meaningful edges, or we can say region boundaries. So here the Hood transform consists of finding all pairs values and which satisfy the equations that pass through x, y. So these are the accumulated in what is basically a two-dimensional diagram. So we plotted these pairs of and x will like a sine wave for all. So you proposed an alternative approach commonly referred to as a Hood transform. So consider a point xi, yi, right? So here is the xy plane, we can see, and in the general equation of the straight line in a slope intercept is of yi is equal to axi plus b. So here this figure A illustrates the geometrical interpretation of the parameters sigma and theta. So horizontal lines here theta is equal to 0° with here in sigma being equal to the positive x intercept. So similarly a vertical line has theta is equal to 90° with sigma being equal to the position respectively y intercept, or theta is equal to minus 90 degree with sigma being equal to the negative y intercept. So here this figure illustrates the huge transform, right? So here figure A shows an image of size 101 by 101 pixels with the 5 labeled points, and figure B shows the each of these points mapped onto a sigma theta plane using subdivisions of 1 unit of the sigma and theta axis. So the range of theta values is plus or minus 90 degree, and range of the sigma axis is plus or minus root 2 dimensional, where d is the distance between the corners in the image. So the points labeled in this figure, the points labeled A here and B show the collinearity detection property of a huge transform. So here point A denotes the intersection of the curves corresponding to the points 1, 2 and 1, 2 and 5 in a XY image plane. So a location of A indicates that the 3 points lie on the straight line passing through the origin and oriented at 45 degree. Similarly, the curves intersecting at a point B in the parameter space indicate the points 2, 3 and 4 lie on a straight line oriented at minus 45 degree and whose distance is from the origin as 71. So finally, the points labeled Q, R and S illustrate the fact that the huge transform exhibits the reflective adjacency relationship at the right and left edges of the parameter space. So here this is the image. So figure A shows the infrared image, figure B is the thresholded gradient image, figure C is a huge transform of this original image and linked pixels we can see here. Now thresholding. So because of intuitive properties of simplicity of implementation and computational speed, image thresholding enjoys a central position in applications of image segmentation. So here the basic of intensity thresholding. So suppose that the intensity histogram in these figures. So here it corresponds to an image of f of xy composed of a light objects on a dark background in such a way that object and background pixels have intensity values grouped into a two dominant models. So on the obvious way to extract the objects from the background is to select a threshold T that separates the modes, then any point xy in the image at which f of xy is greater than t. It is known as the object point. So the point is known as a background point otherwise. But in other words, the segmented image g of xy is given by g of xy is equal to 1 or 0. If f of xy is greater than t, then it is 1. If f of xy is less than equal to t, then 0. So here t is a constant applicable over this an entire image. The process is given in this equation is referred to as a global thresholding. So when the value of t changes over an image, we use the term variable thresholding. So the term local or regional thresholding is used sometimes to denote a variable thresholding which the value of t at any point xy in an image depends on the property of a neighborhood g of xy. So this figure shows a more difficult thresholding problem involving a histogram with the 3 dominant models corresponding. For example, to 2 types of light objects on a dark background, here multiple thresholding classifies a point xy as belonging the background if f of xy is less than equal to t1 to one object class if t1 is less than f of xy less than t2, to the other object class if f of xy is greater than t2. So here the role of illumination. So this figure illustrates the effect that illumination can have on the histogram of an image. So in this figure A is a noisy image from this figure, but D here it shows the histogram. So this image is easily segmented with the single threshold. So we can illustrate the effect of a non-uniform illumination by multiplying the image by a variable intensity function. So such as the intensity ramp in this figure whose histogram is shown here. This figure shows the product of the image and its shading pattern. So here this is the basic global thresholding. So when the intensity distributions of objects and background pixels are sufficiently distinct, it is possible to use the single threshold applicable over the entire image. So in the most applications there is usually enough variability between the image that even if global thresholding is a suitable approach, so an algorithm capable of estimating automatically the threshold value of each image is required. So here we can see the original image and its histogram, and this is the result of global thresholding with T midway between maximum and the minimum gray levels. So this figure shows an example of segmentation based on the threshold estimated using the preceding algorithm. So this figure is the original image and this figure is here it is a image histogram showing the distinct value. So applications of preceding iterative algorithm resulted in the threshold T is equal to 125.4 after after 3 iterations starting with T is equal to M. The average image intensity is M and using del T is equal to 0. So this figure shows the result obtained using T is equal to 125 to segment the original image. So as expected from the clear separation of modes in the histogram, the segmentation between object and background was quite effective. So here is another example, which is the subdivision. So this is a properly and improperly segmented sub images corresponding to the histogram. Now thresholding with optimal global and adaptive thresholding. So this method treats the pixel value as probability density functions. So the goal of this method is to minimize the probability misclassifying pixels as either object or background. So there are two kinds of error: misabling an object pixel's background and misabling a background pixel as object. So this figure shows the gray level probability density functions of two regions in an image, PZ to Z. Another example is use of boundary characteristics. So this is the original image and this image is segmented by local thresholding. It is the color image, right? So this is a segmentation of pixels with colors close to the facial tones and segmented of a red components. So this shows the threshold based on the variables. Thank you.